Good morning. Welcome everyone to the 2016 Restoring the West Conference. Our first speaker this morning is Dr. Rob Davies. He is a Utah-trained physicist and educator whose work focuses on synthesizing and communicating a broad range of research, including climate, energy, agriculture, economics, and complex systems. He has taught on the faculty of 3 universities, worked as a project scientist for Utah State University's Space Dynamics Laboratory, as technical liaison for NASA's International Space Station project, and served as an officer and meteorologist in the United States Air Force. He is an associate of the Utah Climate Center and adjunct professor in Utah State University's Department of Plant, Soils, and Climate. Please welcome Dr. Rob Davies.
Right, well, thanks everybody, and thanks for asking me to be a part of this, Darren. As a physicist, more importantly, as a scientist, as a citizen of Utah and this nation and this planet, let me just say thank you to all of you for the work that you do in making the world more like the place I want to be in. I imagine that as we talk about climate change, and you think about your roles as wildlife managers and ecologists, as restoration ecologists, as foresters, you are probably largely thinking about adaptations to the changes that are coming. And we are transitioning to a new climate system, and so those adaptations are absolutely going to happen one way or another. What I'd like to do, though, in the next 30 minutes or so is redirect the conversation to, as our nation and internationally, as our efforts to mitigate climate change begin to accelerate, to your roles in your jobs and your voices as we mitigate climate change. So to begin that conversation, let me just take a few minutes to remind ourselves what it is we know. And the first thing we know is that the Earth is warming globally. This is what it looks like from the end of the 19th century to today. We know that the planet is warming globally. We know that that warming is not uniform. The high latitudes in the north are warming faster than the rest of the planet. The land is warming faster than the oceans. But if you average it all up, we know that over the last century or so, the planet has warmed up about 1 degree Celsius. When the numbers finally come in at the end of this year, it's likely, now extremely likely, that that number is going to be between 1.2 and 1.3 degrees Celsius. So the warming is substantial and is accelerating. The next thing we know is why the planet is warming, and it's principally from the addition of greenhouse gases to the atmosphere. Now, there are quite a number of these greenhouse gases, but by far the most important and the driver of this whole process is carbon dioxide. The levels have gone up over 50% in the last couple of centuries. Most of that rise has come in the last half century that I've depicted here. The last 50 years or so, we're now at 408 parts per million and continuing to rise. And the reason that these greenhouse gases are rising in the atmosphere is because of us, principally from the burning of fossil fuels, but also due to substantial changes in land systems as well. We know that this human-driven global warming is driving a change in the planetary climate system. Everything is changing. In the atmosphere, whole weather patterns are changing. The hydrologic cycle is intensifying. In the oceans, the waters are acidifying. On land, lots of changes to the biosphere, to ecosystems. And the ice, the cryosphere, is also changing. Not to put too fine a point on it, but it's melting. This is ice sheets, sea ice, glaciers, and even snowpack. And it is this impact to all pieces of the Earth system that we then call global climate change. So human-driven global warming is driving the changes to our planetary climate system. We also know that these changes are having impacts in the physical system to the biosphere. Changes to biodiversity, both on a planetary scale and regionally, namely biodiversity is decreasing, extinction rates are going up. Changes to behaviors, migrations, and the phenology of living systems happening all over, certainly here in Utah, and some of the places on the planet where you're seeing the changes to the biosphere most rapidly are in the mountain regions as you go up in climate systems, as you go up in elevation. And these changes in the physical system and in the biosphere, of course, then propagating their way into the human system, what I sometimes call the anthroposphere. There are now discernible impacts to every major human system. The normal ones that you would think of, food systems and water systems, the health system, as vectors for diseases change their regional range, their geographic range, but also changes that you might not necessarily immediately associate with climate change, such as the movement of humans. The planet now has something like 69 million people who are on the move as refugees. And for a substantial number of those, the changing climate has been a stressor in that, particularly in the Middle East, Northern Africa, and in Europe, as a 4-year intense heat wave and drought crippled the agriculture of Syria, moved large people into the cities, which did not have the infrastructure to handle it and was already not necessarily a stable political regime. Things have cascaded, and climate has certainly been a stressor in that, starting with their drought, their 4-year intense drought. It's worth saying that not only have significant impacts to human systems been observed already, but some of those impacts to some people on the planet have already been catastrophic. There are whole island nations in the Pacific that are preparing to move because storm surges and rising sea levels are driving them out of their home. And that's just one example. The next thing that we know is that as a result of this ongoing human-driven change to the planetary climate system, humanity faces, as we move forward, extreme risks. And we know that by observing the impacts to natural and human systems that have already occurred for the warming we've already experienced, and then trying to use that to calibrate against the warming that and the subsequent climate change that we project going forward. And of course, as we move forward, the anthroposphere, the human systems, is a wholly owned subsidiary of the Earth systems in which it's enveloped. So the idea now is to try to figure out how to mitigate that risk. And we start with I mentioned this notion of projections. So let's just take a look at where we think we're going. This is a temperature projection, and forgive the little cartoon here. It's a thermometer graduated in Fahrenheit. You're welcome. 45 degrees Fahrenheit on the left is the global average temperature at the depth of the last ice age, let's say 15,000 years ago. 75 degrees Fahrenheit on the right is the warmest we think the planet's been ever. That was about 55 million years ago. The green oval represents the climate in which humans and the human ecosystem evolved and has always existed. The region between the two lines is the climate in which human civilization arose and has evolved, to which it is highly adapted and where it has always existed. The purple oval is the projection, the range of global average temperatures we can expect to see by the end of this century. And it's quite a spread, from an additional 3 degrees Fahrenheit to an additional perhaps 14 degrees Fahrenheit global average. And you might say, well, the models aren't maybe particularly good if they're projecting such a spread. It's important to note that while there is uncertainty in our understanding of the physics of the climate system, certainly, and some of the spread in this projection is due to that uncertainty, by far most of the spread in this uncertainty is based on us not knowing how we humans will choose to move forward. So we have to run the models for different scenarios. The lower end of the projections, the lower third of that additional rise in temperature, is for what we would call lower carbon scenarios, where we start moving aggressively away from dumping carbon into the atmosphere. The higher 2/3 of that range of projections for this century is for the higher carbon scenarios. So this is, in my view, good news. It tells us that most of the change to come is still mostly within our ability to control. Nevertheless, we should be very clear that even the low end presents very significant risks for humans. It's moving us out of the climate that we have always inhabited. Some scientists refer to this as moving to a new planet. And there is certainly a difference, though, having said that, between the low end and the high end, the extremes. So let's take a look at what these projections are doing for us, say, here regionally. Temperature-wise, by the end of the century, we're looking at a range of perhaps an additional 4 degrees across most of the continental United States, including Europe, Fahrenheit, rise in temperature, to perhaps an additional 13 degrees Fahrenheit, rise in temperature. And again, the difference here is the scenario that we put into the models, low carbon versus high carbon. And on the right there, the high carbon scenario, those dark red areas represent changes of upwards of 25 degrees Fahrenheit for the Arctic. Here in Utah, of course, and in the west, snowpack is extremely important. This is a spring, what I'm going to show you now, we're looking at here is spring snowpack. When our snowpack is at its maximum, ready to start melting, ready to start feeding the reservoirs. In Utah, of course, most Utahns get most of their water from snowpack in some fashion or other. What I want to show you is the evolution of that snowpack over the last 50 years. So this is where we're going to focus our attention. The darker blues are deeper snowpack. The lighter whites and grays are thin snowpack. We're going to start with observations beginning in 1950. So this will be actual data of how that snowpack is over this time period. And then we're going to look at projections moving forward through the end of the century. So this is how the snowpack evolves. This is actual data. Certainly there's some variability. Some years are snowier than others. That variability actually increases dramatically beginning in the 1980s. And now we're into projections. Not surprisingly, in a warming atmosphere, we're seeing a thinning snowpack. Springtime snowpack. And by the time we get into the latter half of the century, essentially it has disappeared. This is, again, under a high carbon emissions scenario this century, and that is the scenario that we are currently following. I'm going to show you one more projection, set of projections. That's for soil moisture. This takes into account not only changes in temperature, but also changes in precipitation. It's also worth noting that you can get into a kind of a perverse situation where you end up with modestly more precipitation falling in a region and yet drier soil, and that happens because, of course, with higher temperatures, evaporation rates increase as well. This is a moderate emissions scenario. As the places on the map get browner, they're getting drier. As they get bluer, they're getting wetter. Moving into mid-century, significant drying across most of the United States and Central America. And drying through the end of the century, but slowing down, ostensibly under a moderate carbon emission scenario as we get a hold of our emissions. Let's look at that same projection under a high emission scenario. Again, substantial drying through mid-century, and then it really accelerates as we warm towards the end of the century. I'll simply tell you that the people who study these results refer to the scenario on the left as dangerous and the scenario on the right as catastrophic. And again, the scenario on the right is a high emission scenario, the path we're currently following. Okay, so how do we interpret this risk? I'm just going to give you a couple of quotes. This is Lonnie Thompson, quite a distinguished glaciologist at Ohio State University. And this is Kevin Anderson, quite a distinguished carbon modeler in the United Kingdom. Now, what he means by a 4 degrees C future, by the way, in that quote, is that global average warming of 4 degrees Celsius above pre-industrial temperatures. Remember, we've now warmed more than 1 degree Celsius towards that direction. What he means here by the fact that it is unstable is that, like most complex nonlinear physical systems, there are stable points in the way that it can exist. And the physics suggests that as we move between, say, 2 degrees of warming to 4 degrees of warming, there are likely tipping points in the system that make it unstable so that you can't come to rest at 3 degrees Celsius or 4 degrees Celsius. The climate system is then going to move to a very different state, perhaps as much as 8 to 11 degrees Celsius. And it may take a couple of centuries, 2 or 3 centuries to reach that, but you're not going to slow down once you pass those tipping points. And I'd also like to point out this notion that this change of a 4 degrees Celsius world is likely beyond adaptation. And that then takes us into the next point, which is what do we do about this? And I would like to be able to stand here and tell you that these are two of the extreme fringe voices in the climate science community. I'll simply tell you that Lonnie Thompson and Kevin Anderson, the quotes that you have read are extremely common among my colleagues in the climate science community. This is the mainstream view of the risks that we are facing on the current trajectory that we're on this century. Fortunately, there is a plan for managing the risk. There is a roadmap for doing this. And it starts with a pretty simple equation. More carbon equals more risk. We can, using the impacts that we've seen so far, try to identify something that we would call a dangerous line of global warming. The international community has agreed recently in the Paris Accords of last December that we should attempt as a society to keep the amount of total warming below 2 degrees Celsius from pre-industrial temperatures. Again, we've already warmed 1 degree Celsius, a little bit more. And actually, that has been modified and make all efforts to stay below 1.5 degrees Celsius. That's simply because the impacts that have been seen over the last couple of decades have been stronger than were projected originally for the amount of warming that we've already seen. And so it appears that the danger line is maybe a bit less. Nevertheless, we'll use 2 degrees C for this calculation. And from that, you can establish essentially a carbon budget and emission pathway. So how much more carbon can we dump into the atmosphere and how quickly? And stay below that danger line. And here is that budget as of 2010, about 1,000 units of carbon dioxide, 1,000 gigatons of carbon dioxide. That was 2010. We've burned through some of that budget since then. So now here's our budget. On our current patterns of consumption, here's how fast we're going to burn through that budget. About 2 decades. And here's that budget relative to our known reserves of carbon. This is coal, oil, and natural gas that we already know exists. We know where it is, and we know how to dig it up. So our sort of safety budget is about 1/3 of our known existing reserves. Now, this doesn't include non-traditional extraction methods like hydraulic fracturing and tar sands. Of course, we know how to do that. In fact, we are doing that. If we include those reserves, which we should, then our carbon budget is about 1/8 of our known existing reserves. So, from a mitigation standpoint, the task before us is that we have got to move away from burning fossil fuels. We have to do so very quickly. We've got about 2 decades or so, the physics tells us at this point. So, the good news is there are roadmaps for doing this as well, and certainly they are not easy. But the bottom line of the science at this point is this. Dangerous climate disruption, which is 2 degrees Celsius or higher, is underway. At this point on our current trajectory, catastrophic climate disruption is probable this century. And we've got about a 2-decade window for meaningful response. Now, I know what you're thinking. I really hope this guy has not been invited to the pizza party tonight. I get that a lot. And as I said, though, fortunately there are roadmaps for addressing this. And in fact, our society internationally is moving forward, and that motion is accelerating pretty dramatically. Just last week, the first international agreement to start limiting hexafluorocarbons on an international basis, modeled out of a similar way that we limited carbon CFCs in the 1980s. These are extremely powerful greenhouse gases. The international community has now ratified the Paris Accord and been submitting commitments to carbon reductions to try to meet this goal of staying below 2 degrees Celsius of warming, well below. And for the first time ever last week also, the first international agreement on limiting emissions from the aviation industry. None of these things are perfect. But I think the fact that all of this is happening, it's all happening in a relatively short time frame, tells us that the international community is finally getting serious about doing this, and we as a society are doing it. And these efforts are only going to start accelerating. There are a number of pathways that take us there. Demand-side reductions, which means how much we use, are part of it. Essentially, this is efficiency. So, changing LEDs, your incandescents into LEDs, for example. And conservation, which is simply turning off the light. Interestingly, there's a lot to be gained here. For every 10 units of energy we save in our homes, we prevent the need to generate about 130 units of energy due to the inefficiencies and losses in the power system. So there's quite a bit to be saved, to be gained, particularly in the developed world, from efficiencies and conservation. This is part of the roadmap for sure. There are also supply-side moves to make. This is how we produce our power, essentially decarbonizing the grid. And there are quite a number of ways, strategies to do this. Solar power, wind power, geothermal power, certainly all part of that. These are very low carbon technologies. Hydropower, hydrogeneration, dams is also a low carbon technology, and nuclear is also low carbon. And all of these are under discussion as a means to decarbonize our energy use. Then there's the notion of negative emissions. This is actually trying to remove carbon dioxide from the atmosphere. There are quite a number of strategies for this. Afforestation, so introducing forests into places that forests do not currently exist. Reforestation, and various means of soil carbon sequestration. Lots of these strategies involve changes to our agricultural system. And many of you, I'm sure, are familiar with some of these, and certainly this is where you can imagine much of your work being done in the world of mitigation. So taking carbon out of the atmosphere, putting it back into the earth. And then there's a strategy, something called BECCS. This is bioenergy generation with carbon capture and sequestration. The idea here is to grow biological crops, grasses, for example. Certain kinds of grasses have been identified as good varieties on a massive scale, harvesting that, burning it for energy, and capturing the carbon dioxide that's emitted as you burn it, and then sequestering that carbon dioxide deep underground, hopefully where it is mineralized, where you inject it down and it reacts with minerals and just basically turns into rock. And then there are a number of geoengineering techniques that have been proposed. Stratospheric aerosols, injecting stratospheric aerosols, sulfate aerosols into the stratosphere is one technique. What these sulfates do is essentially in the stratosphere form a sort of a reflective, very thin reflective layer that reflects sunlight away from the Earth and tends to cool the planet. And there have been strategies of fertilizing the oceans with iron to stimulate phytoplankton and algae growth, which then, as they grow, suck carbon out of the atmosphere, and then when they die, drift down to the ocean floor and sequester that carbon on the ocean floor. So these are active, what are called geoengineering techniques. All of these things are sort of this menu that the international community is now looking at for ways to mitigate this now extreme risk that we face with a changing climate. Now, as I've been going through these, I imagine some of you have been saying, well, that seems like an interesting idea, and some of you have been saying, with respect to other things, that seems like a really bad idea. And the reason you've been saying that, I suspect, is because you know, and we need to now pay attention to the fact that climate change is not the only large-scale problem we're facing environmentally. It's just one of a whole family of existential threats that we are now facing, all emerging from the same underlying pathology. And to try to get a better handle on that, there have been a number of frameworks to try to start putting the steps we may take into a much bigger context, and that's what I want to talk about. That's mainly what I want to talk about today. One of the most successful of these frameworks has been introduced over the last decade or so by Johan Rockström and his colleagues at the Stockholm Resilience Center. It's called planetary boundaries, and what they've done is identify pieces of the Earth system that they feel are critical to maintaining this relatively stable environmental conditions that we've seen over the last 10,000 years or so in this geologic state we call the Holocene, where we've had this very stable climate. And the notion is that these pieces of the biosphere, these pieces of the Earth system can be disrupted beyond a point at which you start to force the planet outside of the Holocene. Now, climate change in the upper left over there, climate disruption, is certainly one of those pieces of the Earth system the notion is that you can push it so far and then you move out of this stable state. But there are other pieces of the Earth system they've identified as well. Biosphere integrity, for example. Basically, are there enough plants and critters? And there's a couple of different flavors of this. There's genetic diversity, so just the total number of species that we have, but also the notion of functional diversity. Do you have enough of a certain kind of a species in the ecosystem to do its job? Or has it become essentially functionally extinct, even if there are still a few remnants, individuals around? Changes to the land system, which they have quantified by looking at the percentage of remaining forests, tropical and mid-latitude, and also boreal forests. The use of fresh water, this includes both consumption, human consumption, and also how much you divert from different watersheds such that the flow of the water can no longer support the ecosystem that it had been. They're looking at biogeochemical flows, in particular phosphorus and nitrogen. in the Earth system. The introduction of novel entities, stuff that really shouldn't be there. So these are the host of tens of thousands of synthetic chemicals that humans have introduced into the biosphere that were not there when all of us and our ancestors evolved, and the risks that they pose. Stratospheric ozone depletion speaks for itself. I think we're all familiar with that. Atmospheric aerosol loading. This is how much junk you put up in the atmosphere, and this can have particularly strong impacts on regional climates. Already evidence that the aerosol loading in Southeast Asia is disrupting the East Asian monsoon. And then the notion of ocean acidification as well. What they've done is take all of these parameters and kind of try to start quantifying how much have we perturbed the steady state of these parameters, and kind of given us a radial scale. And in this scale, we're going to put down two lines. One is the blue line is sort of the safety zone. We don't impact it. We want our impact to stay below the blue line. The region between the blue line and the red line is sort of we think we're in a gray area here, approaching danger. And if you've pushed that particular Earth system beyond the red line, then there's strong evidence to suggest that that's really not at all safe, and that done long enough is going to push the Earth out of this Holocene state. And with climate disruption, so where you want to stay is in the green. You really don't want to be in the yellow, and you definitely don't want to be in the red on this scale. With climate disruption, our best ability to quantify this suggests that we are past the safe zone and into the gray area. And then we can do this, or Rockstrom and his colleagues, and quite a number of groups around the country have done this for as many of these categories as they can. Some of them they've not figured out yet how to quantify. And when you do that, you get something that looks like this. And you see that we have far breached some of the safety lines that this framework has set in terms of genetic diversity. In other words, the extinction rate has gone through the roof. We're very close to the danger line on changes to the land system, particularly the forests, and we've blown through what we think the sustainable line is for the Holocene in terms of nitrogen and phosphorus cycling through the Earth system, largely through our industrial agricultural system. And then there are other things where we're close, such as ocean acidification, etc. So the notion here then is simply that this gives us, climate change is certainly something we need to be trying to mitigate, but it's one of a family of things. And certainly these planetary boundaries are not individual. They all are interconnected. Some of them make much more sense to talk about on regional, even very local levels like watersheds. Some of them make more sense to talk about on whole global levels. It's a complex framework, but turning out to be quite a useful one. And in particular, useful for figuring out, well, as we decide to move forward for climate change, how do we think that affects some of our impacts in these other areas? So for example, demand side reduction. If we just get more efficient and we try to use less, do more with less, certainly from a climate change perspective and something that goes right along with that, ocean acidification, that would seem to be a net positive. The idea is that we want to make changes that are synergistically beneficial to these other challenges that we face and not exacerbating those challenges. And biodiversity hopefully also affected if we just use less energy. Changing our supply, for example, decarbonizing our supply. I mentioned solar, wind, and geothermal. Well, again, almost certainly a good deal for climate change and for ocean acidification, but maybe a mixed bag for land system changes, depending on how you deploy wind systems and solar systems. Are solar systems deployed as massive centralized structures in disrupting whole biomes? Or are they more distributed, just put up in smaller structures in many more locations? That can have an effect as to how it's changing your land systems. Building large dams, great idea from the standpoint of decarbonizing your power system, terrible idea from the standpoint of impacts to ecosystems, as many of you in this room I'm sure are aware, and the same goes for nuclear. This notion of negative emissions, afforestation, reforestation, sequestering carbon, again, probably a good thing for biogeochemical flows, for changes to your land system, the biosphere integrity, and for climate change and ocean acidification. This notion of BECCS, though, growing huge monoculture crops over land areas rivaling between 1 and 2 sizes the size of India, 2 times the size of India, likely has detrimental impacts to this notion of biogeochemical flows, phosphorus and nitrogen, extremely detrimental. Changes to the land system, introducing these big monocultures, and the effects, the knock-on effects that has to biodiversity. So we can continue this with this entire menu, and as you start to fit climate change into this framework, it starts to help us see what are maybe the better pathways as we move forward in trying to make this mitigation. We can probably say that hydro and nuclear are not the best options when you're considering things more than just carbon. This notion of bioenergy production with carbon capture and sequestration, also not maybe such a good idea from the standpoint of the other environmental challenges we're facing. And with this notion of geoengineering, by the way, those are just terrible ideas. We stopped putting sulfate aerosols in the atmosphere because it produces acid rain. And now the suggestion is we start injecting it into the atmosphere to screen the sun. Well, the acid rain's going to come back. And there are all kinds of unknown problems with just making these massive changes, iron fertilization of the oceans as well. Who thinks it's a good idea to just dump this in there and induce a massive change to the marine ecosystem with just the notion of pulling out carbon? Sure, it'll do that, but what else will it do? So from a risk standpoint, we can start to maybe make these changes. The planetary boundaries framework can maybe be thought of as trying to identify a ceiling. The Earth system is this roof that protects us from the universe, and we need a good solid roof. Now, where we've busted through that roof, we've now started to sprung leaks. And we can identify in a much more holistic fashion which pathways we can take forward with respect to climate mitigation that start to repair that roof, and which pathways actually make those holes bigger and bust new holes in there. I want to close with just the notion that one can make the same sort of arguments, not just with the planetary boundaries forming a roof, but also with this notion of a social foundation, how we move forward societally, trying to provide food, water, and vitality to the world's people. And as we do that, by providing education, by providing energy, healthcare, etc., as we consume resources to build this solid social foundation, of course, that's what's eating into our protective roof of these planetary boundaries. At the moment, this is what we would like it to look like, a solid foundation and a solid roof. At the moment, it looks more like this. We've got holes in the roof and big holes in the social foundation. Tens of millions, hundreds of millions of people across the planet who don't get enough to eat, who don't have access to the energy they need, to the health care, to the education, etc., etc. And so some of those pathways to mitigating climate change are synergistic with building that social foundation as well. Some of those pathways are exacerbate efforts to build this social foundation as well. So as we move forward, the final point that I want to get to here is that as you move forward in your roles as restoration ecologists, and foresters, and wildlife managers, and you think about mitigating and what you might be doing in your field to start mitigating climate change, it's also important that your voices are heard at the table when ideas come up that are maybe not such a good idea from the standpoint of ecosystem services, let's say. And it's also important that you be aware of some of the things that you may be thinking about doing that are not such a good idea from the standpoint of climate, or from the standpoint of biodiversity, or from the standpoint of building a solid social foundation as well. We no longer have the luxury of going about our work to fixing these problems in isolation, blind to the bigger picture. We absolutely have to move forward with the much bigger picture in mind. And if we can do that, of course, the idea is to build this, and I'm asking for your forgiveness before I even show this. This sort of, what has been articulated as a safe and just and equitable space for humanity. And so certainly as you think about adapting to climate change, be aware that there are large-scale efforts now to start mitigating climate change. And some of those are good ideas synergistically for this host of problems that we're looking at. Some of them are not such good ideas. And I think it's important that we move forward with that in mind. So thank you very much for your attention. minutes for questions. Yes? Sure. Right. So the notion is climate. You hear this a lot in my business. Climate changes, always has, always will. No question about it. And the glacial, interglacial cycles, the ice ages, are a good example of that. We understand what brings on the pretty well, what triggers ice ages and what triggers interglacial periods. It has to do with changes in Earth's orbital parameters. There are 3 specific parameters. I won't go into them right now, but they change. We understand them really well. And they change on timescales ranging from about 40,000 years to about 140,000 years. So the onset of an ice age takes a good 30,000, 40,000 years. And the coming up out of an ice age into an interglacial takes a good 10,000 or 15,000 years. So the short answer is these processes are still ongoing, certainly. But they don't operate on human timescales. They operate on timescales of tens of millennia. And so certainly there are tugs in the climate system now that are moving us towards an ice age, but they move very, very slowly. You know, in another 15,000 years, remember human civilization is only 8,000 or 10,000 years old, we can expect to start moving into another ice age very gradually. The processes that we're talking about the climate change that's going on right now are happening much, much faster, on the order of decades. Okay, and so that's what we're talking about. One more question, maybe. Yes?
Solar flares, how does that affect the atmosphere?
Solar activity. So solar flares, in terms of climate, basically not at all. I mean, flares happen sort of irregularly, and they happen and they're done. But that said, there are cycles to the sun. These are, we call them solar cycles, the appearance and disappearance of sunspots, which does lead to a slight brightening of the sun and a slight dimming of the sun. Counterintuitively, when you get more sunspots, you've got a little bit more solar energy coming out of the sun, on the order of just a few hundredths of a percent. That happens quite regularly, and we track them. It's about an 11-year cycle. And so what you find is you get the sunspots coming on, you get a few hundredths of a percent brightening of the sun, and as they go away, a few hundredths of a percent dimming. But taken on average, let's say over the last 50 or 60 years, for which we have really good data on these, the energy coming from the sun is extremely steady. You know, if you just average out those little 11-year ripples. So, in fact, it's going down slightly. So the solar energy tug, long-term solar energy club tug, the multi-decadal solar energy tug on the climate system right now is slightly negative, tending to cool us just slightly.
Thank you, Rob.
Okay, thank you.
Good morning. Welcome, everyone, to the 2016 Restoring the West Conference. Our first speaker this morning is Dr. Rob Davies. He is a Utah-trained physicist and educator whose work focuses on synthesizing and communicating a broad range of research, including climate, energy, agriculture, economics, and complex systems. He has taught on the faculty of 3 universities, worked as a project scientist for Utah State University's Space Dynamics Laboratory, as technical liaison for NASA's International Space Station project, and served as an officer and meteorologist in the United States Air Force. He is an associate of the Utah Climate Center and adjunct professor in Utah State University's Department of Plant, Soils, and Climate. Please welcome Dr. Rob Davies.
Last couple of centuries, most of that rise has come in the last half century that I've depicted here. The last 50 years or so, we're now at 408 parts per million and continuing to rise. And the reason that these greenhouse gases are rising in the atmosphere is because of us, principally from the burning of fossil fuels, but also due to substantial changes in land systems as well. We know that this human-driven global warming is driving a change in the planetary climate system. Everything is changing. In the atmosphere, whole weather patterns are changing. The hydrologic cycle is intensifying. In the oceans, the waters are acidifying. On land, lots of changes to the biosphere. So those adaptations are absolutely going to happen, one way or another. What I'd like to do, though, in the next 30 minutes or so is redirect the conversation to, as our nation and internationally, as our efforts to mitigate climate change begin to accelerate, to your roles in your jobs and your voices as we mitigate climate change. So to begin that conversation, let me just take a few minutes to remind ourselves what it is we know. And the first thing we know is that the Earth is warming globally. This is what it looks like from the end of the 19th century to today. We know that the planet is warming globally. We know that that warming is not uniform. Right, well, thanks, everybody. And thanks for asking me to be a part of this, Darren. As a physicist, more importantly, as a scientist, as a citizen of Utah and this nation and this planet, let me just say thank you to all of you for the work that you do in making the world more like the place I want to be in. I imagine that as we talk about climate change and you think about your roles as wildlife managers and ecologists, as restoration ecologists, as foresters, you are probably largely thinking about adaptations to the changes that are coming. And we are transitioning to a new climate system. In some form, the high latitudes in the north are warming faster than the rest of the planet. The land is warming faster than the oceans. But if you average it all up, we know that over the last century or so, the planet has warmed up about 1 degree Celsius. When the numbers finally come in at the end of this year, it's likely, now extremely likely, that that number is going to be between 1.2 and 1.3 degrees Celsius. So the warming is substantial and is accelerating. The next thing we know is why the planet is warming. And it's principally from the addition of greenhouse gases to the atmosphere. Now, there are quite a number of these greenhouse gases, but by far the most important and the driver of this whole process is carbon dioxide. The levels have gone up over 50% in the last